Welcome to session 11 for OMIS 302, Introduction to Production Management. Today we want to look at the second part of project scheduling, which specifically has to do with the unique type of projects. We said that project managers undertake several types or kinds of projects in their work. And in production, there are certain projects that are routine in nature or repetitive that we keep doing day in, day out. And so those ones we use what we call a deterministic approach, which was what we saw in the previous session as the CPM, or the critical path method. Now we want to look at this other technique, which we call the project evaluation review technique, which is the PERT. So it's a technique developed to handle uncertainties in project completion times. So for instance, there can be uncertainties when you do not know exactly how long it would take to complete a certain task or a certain activity, especially when it's the kind of project or activity that you've never undertaken before, or it's a new kind of project. So for instance, if you are, let's say, an event organizer, and you're used to organizing weddings and birthday parties and all sorts of events. Now, supposing you're supposed to organize a football game between star artists, and then football starts in the country, which you've never done before, you could be a little skeptical about how long it would take you to even assemble the kind of stars you want on the various teams and a whole lot of activities. So normally, these kind of projects also are treated in a different way. And the technique we use is the project evaluation review technique, which we said normally designed to handle uncertainties in projects. Now, under the PERT, we would use what we call 3-time estimates, what we call the optimistic, the most probable times, and then the pessimistic time. And I'm sure by now we understand what optimistic and most probable and pessimistic would be. When we talk of the optimistic time, optimistic is just looking at some very positive dimension of what will happen, and the pessimistic looks at the kind of negative dimension or negative side of the situation. And then the most probable looks at a combination of both scenarios, both the pessimistic and the optimistic. Now, for instance, if you were to travel on a bus from University of Ghana campus to Central Accra on a Sunday, you could have one person telling you, well, if you're interested in knowing on the average how long it would take me to move from Legon campus to Accra on a Sunday, someone could tell you, well, it's a Sunday, people are not going to work, so, well, I'm sure the road will be free, and so I am super positive that it will take you 5 minutes. That is a very optimistic person. He's sure, and well, of course, that is the case. On Sundays, there isn't traffic on the road, so it should take you the least possible time to get to Accra. You could also have another person who is very negative, a very pessimistic person, who could also say that, well, I understand, it's a Sunday. How about if there is an accident in the road, or the road is being closed for some repair works or something, that you may have to use some alternative routes that could make your journey longer. And so he thinks it could take you 20 minutes. So that is someone who is also so negative and wouldn't look at the bright side of things because it's a Sunday. And well, but it doesn't mean he could be wrong. He could be right. And so the most probable would say, well, I think both guys are correct. It is Sunday. There would be no traffic, and you could get it that easy. It could also be the case where the road could be closed, or there could be some broken down vehicle in the road, and so probably you may have to wait some time to get your turn to pass, and all this. So how about we say it could take us 10 minutes? The most probable time considers the case of the pessimistic and the case of the optimistic and puts them together and kind of finds the situation. So we are going to consider these 3-time estimates: the optimistic time, the pessimistic time, and then the most probable time, and then find an average time, or what we call an expected time for an expected duration for each activity. Okay, so we use a mathematical expression which says A plus 4 times M plus B over 6. A standing for the optimistic time, and then B standing for the pessimistic time. You know, kind of have this funny feeling that if you turn the B upside down, if you turn the B upside down, you could probably get a P. You know, you turn it left, right, upside down, you get a P. You know, so that's kind of say it's pessimistic. And then if you took out the tail of the A, you have an O, and then funny, that could make it. So yeah, so that's just kind of some, and then M for the obvious. What's it called? The obvious. What's it called? Most likely. So we take now. What we do is, because you're a rational human being and want to make the decision based on the most likely time to occur, we kind of use a weighted average approach. And so you say A plus 4M plus B divided by 6. The 6 is the total sum of the weights attributed to each of the parameters above. So what we are saying, we are giving the optimistic time a weight of 1, and then the pessimistic time also a weight of 1. But we are giving the most likely time a weight of 4, which is saying you're placing more emphasis on the most likely time because it takes into consideration what is happening from the pessimistic point of view and what is happening on the optimistic point of view, put them together. Okay, so that's how come we are dividing both by 6. So A has let's say a coefficient of 1 or a weight of 1. B also has a coefficient of 1. And then M has a weight of 4. So 1 plus 4 plus 1, that is 6. So we just do that. Okay, so that's just how we used to find the expected time. The difference between the PET or the PERT and then the CPM is that the CPM, like I said before, is a deterministic technique. It is used for those projects that are routine in nature or repetitive. And so the project manager or the production manager actually has a good idea of how much time it takes each activity and can readily tell. But the PERT, because with the elements of uncertainty you cannot tell, we want to take, we use what we call the expected time. So we say that the PERT is more probabilistic. So we base our time estimate. That's why we say it's an expected time. Okay, so we take 3 time estimates and take a weighted average of the 3 time estimates. And so this time around, you notice that in any question or when you're faced, we have a pessimistic, most likely time, and then the optimistic time. We take the average, we sum these 3 time estimates, multiply the most likely one or the most probable one by 4, and we divide by 6. Now, anything that has an average, because it is an expected time, chances are that we could get it right or we could get it wrong. And that brings in the idea of deviations, okay, or what we call the variance. So we also have a way of finding the variance so that we can find the standard deviation of, so we know how far or near we are from the actual time or the distance. And so to find our variance, we say our variance is the optimistic time minus the pessimistic time. Sorry, the pessimistic time minus the optimistic time divided by 6, and then you square that ratio. Okay, that is the variance. And obviously the standard deviation will be the square root of our variance. So it's that easy. Every other thing apart from computing the expected time and then the variance for this kind of situation, it remains the same. Okay, so in determining our critical path, we follow the same procedure like we did before in the previous video, where after the only difference here is that this time, before we want to draw our network diagram, we must first compute the expected time for each activity. And so you take for each activity the pessimistic, optimistic, and most likely time. You do your A plus 4M plus B all divided by 6 for each activity to find the expected time for each activity. Then you draw your network diagram like we did before. You do your forward pass, you do your backward pass, then you do your latest finish minus your earliest finish, or your latest start minus your earliest start to find your slacks. And all those activities that have slacks of 0 are the critical activities. You connect an arrow from the beginning to the end and you find your critical path. It's that easy. Nothing is different in finding the critical path like we've seen already. Okay, so in computing your variability, we will want to assess our variability. We assume that the project completion time is normally distributed like any other probability distribution. Okay, so here we use what we call the standard normal distribution to actually assess our variability. And I'm pretty sure we've seen, lots of us would have seen this computation in quantitative methods where we use the z-score, or we convert it to the z-score, which is the standard form for the probability distribution. Okay, so we say that the variability in a critical path or set of activities can cause variation in the project completion time. So, but the variation in non-criticality ordinarily has no effect. And so you want to be that sure that your activities, what you are getting, the answers you're getting for your slacks are that correct. So we normally would use our critical activities to compute the variability in the project completion time, to find out by what is the chance or probability of we missing the target or hitting that target. Now you should understand this. You should understand that when you get a wrong project completion time, well, fine. If we finish before our expected, whatever the project completion time is, well, we wouldn't have too much of issues to deal with. But if you get your completion time wrong and we go beyond that, then that is where the project is going to experience cost overruns, because you're going to be going beyond the estimated time. And then in that case, you would actually be looking at hiring extra people, or probably paying for extended time periods, and that will come at extra cost. And so we are interested in finding the variability in the critical path activities. And so the first bullet is that saying that variability in our critical path activities can cause variation in the project completion time. And so we want to, and so we're just going to go through the same procedure and understand this same, what's it called, technique. So in finding our variability, or the probability that we could meet or exceed our project completion time, we just need to find our standard deviation. And just like the same thing we do under standard normal distribution, we take the what's it called, the sample mean minus the population mean all over the standard deviation, and you find your z-score, you use your z distribution table, and then you find your probability from the distribution table. Yes, that easy. Okay, so we say that we assume that t is normally distributed, or the expected times are normally distributed. So the probability of meeting a specified project completion date can be computed as the d would be the duration, and then e will be the expected time, and then our standard deviation would be the square root of the variance that we'll compute, which we said was the b minus a over 6, and you square whatever you get from that ratio. So z is going to be the computed value to read from the standard normal probability table. So here you need to know how to read the standard normal probability table.